So let's say we are looking at the example where we have the system x prime equals 0, 1, 1, alpha x. So we have one unknown constant in this system, but alpha is still a constant. So where alpha equals a constant. Okay. So depending on what alphas we use, we're going to get different eigenvalues, right? So if, let's for example, say we do alpha of 0, then we are going to get eigenvalues of plus or minus I. But instead, if alpha is 3, our eigenvalues are 1/2 times 3 plus or minus the square root of 5. So what's interesting is depending on our value of alpha, we have either complex or real eigenvalues, right? But the thing is that distinction between complex and real is pretty important because of the fact that we get very different forms for our general solution, and then the behavior is different, right? Are we going to have that spiraling or not? So the question is like, can we find the point where we switch between the real and the complex? So that's going to be our goal. Can we find that point? Any ideas how we can do that besides guessing and checking? How do we find eigenvalues? Yeah, perfect. So we take the determinant of A minus lambda I, so that's lambda times the identity matrix, right? So in this case, we have the determinant of negative lambda. Ooh. The upper right-hand entry should have been a -1 on that matrix. So right here, that is not what I wanted, right here. So we have negative lambda, -1, 1, and then alpha minus lambda. Do I take a determinant of a 2 by 2? Yeah, AD minus BC. So we do the one diagonal minus the other diagonal. So I'm going to have negative lambda times alpha minus lambda minus 1 times -1. And then if I clean this up, I've got lambda squared minus alpha lambda plus 1. And to find our eigenvalues, we set this equal to 0. All right. What do you want me to do now? Maybe, but I really want to focus in on those eigenvalues. So let's stay focused on how I could find the eigenvalues. I know there's an alpha in here, but could we find the eigenvalues of this? Quadratic formula, our favorite thing ever, right? So if we use our quadratic formula, we have the opposite of b, so that's going to be alpha plus or minus the square root of negative alpha squared minus 4 times 1 times 1 all over 2 times 1. Which gives me alpha plus or minus the square root of alpha squared minus 4 over 2. Okay. That's my eigenvalues for the system. Can't simplify it anymore. So that's what we've got. Okay. Can you make any conclusion about if these eigenvalues are going to be positive or negative, or not eigenvalues? If they're going to be imaginary or complex? Those are the same thing. Complex or real? Yeah.
So alpha is greater than 2.
Ooh.
Real, and it's less than 2.
Yeah. How'd you get that?
I was looking at this quadratic formula right here. You got the a squared times 4. And I know I is equal to square root of -1.
Yeah.
So it's square.
Perfect. So if what's underneath the square root, which in this case is alpha squared minus 4, is greater than 0, then your eigenvalues are real. And then if alpha squared minus 4 is less than 0, then your eigenvalues are complex. And then if it's equal to 0, you have a repeat eigenvalue. Okay. So Theo did it all in his head, which is amazing, but I have to draw myself a little diagram sometimes. So I know the roots of alpha squared minus 4 are -2 and 2. And so if I picked something between -2 and 2, I would have alpha squared. I'd have something less than 4 and be subtracting 4. So I would get a negative. Yeah. And then on either side, I would have positives. But it could have been flip-flopped just depending on how we had set up this equation. So what we know is at plus or minus 2, the eigenvalues change from real to complex, right? So in this section, they would be complex, and then they would be real at less than -2 and real at greater than 2. So this point as a bifurcation value. So I think that's something really cool that we don't know everything about the system, but we can at least know like when that system is going to change depending on what the alpha is. All right. What are your questions about that? Or does that feel pretty good? Awesome. So what I'd love for you to do on your own paper, collaborating together, just figuring it out, you're not turning this in, but I'd love for you to think about this, is can you find a matrix with an alpha, but no bifurcation value? So think through like, how would you solve that? Okay. So in other words, this matrix is always going to have real or always going to have complex eigenvalues. Oh.
I'm not enough on. My brain's immediately thinking like, cost, energy. One good find, maybe guys.
Just reinforce things.
You were gonna guess and check, back corner, I think you're employing some linear algebra.
Find one that's always.
Or real, you can do.
Oh, the real.
Okay, I love it, let's change it up to always complex. Which is good, because I do have one that's always complex. You think about it. Sure.
So it is possible.
It's definitely possible. And if you're real, it's easy. Have you talked at all about diagonal matrices? Right? What's special about that?
If the eigenvalues are on with that.
Right.
Oh, so A is just gonna be whatever you put there
Yeah, also,
throughout.
a property, when you have a, what we call an upper triangular matrix.
Yeah.
Right, the eigenvalues of upper triangulars are also along the diagonal, so this would be another
Right,
one.
is the-
Mhm.
Honestly, it is everywhere.
I've been plugging an eyebrow, just the way to count for right now.
Let's keep alpha real for now. You can do it when alpha is real. So I think something you could maybe try is maybe try like working back from your quadratic equation. Right? That's one way you could approach this.
So I'm trying to catch up.
Yeah.
So I feel like I got some, but when it comes to then plotting it, how do we plot if our initial conditions? It's like before we had,
Mhm.
a different problem where we were plugging in.
Yeah, so I think about, we're not really plotting, instead of plotting our solution where we have like, because we do have a T underlying all of this. So instead of like plotting this solution, when I'm asking you to plot the trajectory, and we're talking about the phase portraits, you're gonna have like X1, X2. So do you have that Mathematica file I sent it? Okay. So in this file, I did one where you can change this point. And this gives you the trajectory starting at that point.
And so, okay, so that is the point about plugging.
Yeah.
Okay.
The only thing you have to be careful of is the way Mathematica does string points in the vector one, is it does backfill, but you're not supposed to backfill. So you would start here and then.
Okay. Always goes. I have a question.
Yeah.
So.
It's not great. Well, it's not great for myself.
Interesting.
I don't know why, but like, I feel like he's thinking what he wants. He doesn't have nothing, you know.
I can hang on the bar and like completely straight.
Yeah.
Up and down like that all day long. Like, but really, upside down.
I agree with you. Oh, you're positive.
It works a lot more. A lot of people don't. Or possible.
I have a question. Instead of just having
Girlfriend.
an alpha,
Yeah.
square up here. That was
That's the first thing that I just people off. You can just right back out, so it's.
enable that to make sure. it
That's
was
a good thing, you know, there's something.
positive.
I think I'm going to learn that. Well, yeah, no, it is successful. I was happy with that. retest the forward and all forward and spin and with the next step. No point, I should cut one out. I was used to telling you.
Yeah, I was.
Okay, Theo had an interesting one. He was going for always complex. What was your matrix again? Right, so 0, alpha, -1, 0. So this is always complex eigenvalues when alpha was a positive real number, is what Theo found. So that's a pretty cool one. That's pretty close. So the one that I found, I did cheat a little bit and I didn't tell you. In order to do it, I actually had to use 2 alphas. So where did I put it? It was alpha 1, -1, alpha. This one is always complex. And the reason that this one works is when you take the determinant, you get, when you take the determinant of A minus lambda I, why does this keep shutting off today? You get lambda squared minus 2 alpha lambda plus alpha squared plus 1. So in your quadratic formula, you get 2 alpha plus or minus the square root of -2 alpha squared minus 4 alpha squared plus 1, because your C value is actually alpha squared plus 1 over 2 times 1. And when you expand that a little bit, you get 2 alpha plus or minus the square root of 4 alpha squared minus 4 alpha squared minus 4 over 2. So those 4 alpha squareds canceled out and you're left with a -4 under your square root. It might be possible to do it with 1. I just haven't found it yet. So that would be an interesting question. All right. Any other questions about this? Okay, so a little bit of a weird week, and Dr. Thomas is actually going to be with you guys on Friday, and you have a quiz on Friday. I think I didn't hear her say it, but when she walked in, a couple people said she was going to do problem 2 from the midterm to retest, is what they heard. And homework is due Monday. I'll take your in-class assignment now if you want to turn it in. Otherwise, Monday as well, and I'll come to class on Monday to pick them up. Okay. The only time probably that arrows or like I think this is that it shows what direction you're it's already so
But this is a-
yeah.
Here today, like the computer.
If she's here today, I mean, they're having an apartment.
Okay. So how time is turned on?
1 alpha. Do like 0 alpha, or yeah, 0 alpha, alpha 0 to make it what's real.
Yeah.
Yeah. The only, so you, in that case, you would have repeated eigenvalues, I think. So it would be always real, but it would be different from the unique eigenvalues case that we've been talking about.